Let's look at a practical application of clustering methods. Clustering. Now, the essence of this is to cluster individuals, in our case, investors, based on their demographics and several other factors. There are several clustering methods. We are going to try a number of these clustering methods, but in the process, we shall do a lot of EDAs, exploratory data analysis. I want you to know that you can create content in Python. So if you want to create content, you could do it like this. It is one of the ways you can be creating content. Okay. So that even if you send it to an HTML file, you can easily move in between them. So if you double click on this, you will see that we have #0, which it represents the 1.0. In this case, it's a problem definition. You put a square bracket between the 1 point and then the name, the title of what you want to say. After the 2 square brackets, outside the square bracket, you put in a bracket, and inside it, you write hash and whatever number. Python always starts from 0. So you can see that the main content here is going to be for the 0, 1, and the others will follow like that. But for the English writing app, the main content is going to be from 1. So just so you know that you can always create content information. We're going to look at all of these as it relates to clustering. So let's try to understand the problem at hand. What is a problem? Well, the aim of this study is to build a machine learning model that will cluster investors based on the parameters related to the ability and willingness to take risks. So you have thousands and millions of investors, and you want to be able to help each one, but there are so many. There's so many. So if you don't build some clustering, you will not know what to do. Most of the time, each one of them will have, some group of people will have similar desires. They are investing for a certain purpose. Then you can cluster the purposes together, and you might get a group of purposes. In this case, it is related to the ability and the willingness to take risks. And we are going to, use common demographic, financial characteristics of these people to achieve whether or not they can take risks. Now, the data is coming from a survey of consumer finances, which is conducted by the Federal Reserve Board, which has been used in several other cases. In fact, we shall use some of those cases next week in a different setup, in stock market valuation. Now, the survey is coming from answers from 10,000 plus people in 2007. That was before the financial crisis. And 2009, which is after the financial crisis. There are so many factors that individuals responded to, or that the questioner demanded that they supply. And those features were consolidated into over 500 features. That's a lot of features. In fact, if we were to do regression, we are talking about a lot of independent variables. Now, because the data has many variables here, the first sensible thing to do is to cut down the number of variables. 500 plus is too much. Then you select the most intuitive features that are connected to investors' ability and willingness to take risks. So if you had a data set like that, that's what you would have done originally. You would have actually, combine this data, cut it down, and then select those that are connected to investors' ability. And again, that is a kind of higher form of grouping. So if you look at the entire data, we have more than 500 features. When you look at academic literature and industry practice, okay, they will tell you that the risk tolerance is heavily influenced by three major factors. The major factors are demographic factors, financial attributes, and behavioral attributes. So demographic attributes could be age, current income, financial, net worth, behavioral, willingness to take risks, and so forth. All of these attributes were available in the data set and they have been summarized. So it's like the first part of the work, which you would have done and of course, this would normally take a longer time and a team of, investor team managers. They will do that together. So in real market systems, you will take some time to do that category. You might get even more than demographic, financial, or behavioral. Now, in the data set, every column you will see is a numeric variable, which is corresponding to the value of the attribute. So based on the questionnaire, you have given a numerical value to it. And these attributes can be summarized as demographic, financial, and behavioral. So here are some of the factors. You see, it's very important that before you do your thesis, dissertation, what else, project, anything else, before you do that, you got to fully understand the variables you are collecting. And I'm sure, Godwin, you will understand it. When I used to say that we need to know what is really the definition of the variable.
Yes, please.
If we say that you are using corruption, what kind of corruption? Is it incidence of corruption or is it corruption reduction? Is it corruption perception index? Is it, so we got to understand when you say performance, what is the specific? Don't say I want to look at performance. No. Performance what? What is the measure of performance? Is it a return on assets? Is it a return on equity? Is it the net interest margin? Is it the Tobin scale? Is it DEA measures of frontier efficiency? You got to be very explicit. And that is it. So when the data is given to you, or before you collect the data, you got to know exactly what data you're picking. In this case, the behavioral attribute or the demographic or financial are as follows. Out of the 500, we have the following. Age. So age, there are 6 age groups. If the person is, below 35 years old, the person is given an age group of 1. If the person is more than 75 years, the person is classified into the age group of 6. So in between the 35 and 75, there are different classes of age groups that are there. You have that in the data set. Well, later on we show the data you see, but let me just quickly steal some features. So when you go to age, if you look at age, you might think that, oh, this is 3-year-old person, 7 years. No. It's not 3 years. It is an age classification for a person potentially between the age of 40 to 55. So there are different classifications of age. Whereas this one might be from 55 to 60 or something. So that is the classification. So now you are getting the age, information. The next thing is education. But all of the variables are like that. So there are 4 categories of education. If the person is given an educational category of 1, it shows that the person has no school at all. He's not been to school. If the person is having 4, classification of 4, it means that that person has a college degree. Whether it's master's, whether it's undergrad, whether it's PhD, it doesn't matter. He has a college degree. So you can see that the in-between will be those who have gotten, you know, what do you call it? High, between those who have gotten lower school and those who have gotten high school. That's what it will mean. And then the one will be those who have gotten no school at all. But you can see that this one, the one is those who have gotten no high school. Okay. So maybe those number 2 will be those with high school and then college and then above college or something like that. So when it comes to education too, and you come and check the value of education, and you realize that the education is 2, is 1, it doesn't mean that a person has 2 years of education, because now you understand what it means. Married. There are 2 categories, okay, to represent the marital status. 1 represents the person is married, 2 represent the person is unmarried. So we don't have divorced, widowed, or any of those. All of that are unmarried. Then we have number of children. So, because you see, before a person will invest, all of these factors, age, education, marital status, kids, and all of that, they'll come into the picture. Anyway, so all of this will form into number of children you see. So if the person has 1 child, and you will see that most of these people, look at the kids section, most of these people, they don't really have children. And they are the ones who are ambitious, you know, to make some heavy investment. 2 children, 1 child, no child, and things like that. Then we go to life cycle. The life cycle variable is used to represent a person's ability to take on the risks. So now we have moved from the demographic to the financial. Now, there are 6 categories in increasing level of ability to take risks. So a value of 1 represents a person age under 55 who is not married and has no kids. So look at that. That is a life cycle variable. Because your ability to take risks will be dependent on that. And such a person is given a value of 1. But when you have a value of 6, it's serious, because it means that you are over 55. Normally, such people don't want to take risks because they are thinking of potential death. What am I going to do and all that? They are not working. So again, their level, they have an increasing level of ability to take risks. And when you have children, okay, and you are driving, you will notice that the way you will drive will be different from when you don't have a child. Be very, very careful about the way you are driving. So all of these factors will play a role. Occupation, okay, the occupation category, OCC 80, is 1 if the person is in a managerial status, okay, and 4 if the person is unemployed. So if a person is unemployed, how is that going to affect the person's investment? And if the person is in a high managerial status too, how is that going to affect? That is it. Then you have risks, the willingness to take risks, which is on a scale of 1 to 4. 1 represents that the person has got highest level of willingness to take risks. Okay. And 4, the person has no level of taking risks at all. Now you go to, and these are still financial, okay, housing, okay. It shows whether the individual owns a house, is a homeowner. If it is 1, it implies that the person does own a home. If it is 0, the person owns no home. That will affect the person's, investment situation. Then the W saved represents the individual spending versus income. It is split into 3 categories. For example, 1 shows a person spending exceeding his income. Okay. And then 2 might be a person who's spending does not or is equal to his income. And then the 3 might be a person whose spending is lower than his income. All of this will affect. The spend more represents a higher spending preference if an asset appreciated on a scale of 1 to 5. And then the person will now decay. Then the WNW cut, which is a behavioral thing, will represent the net worth category. There are 5 categories. 1 shows the net worth is less than 25th percentile, and 5 will show the net worth is more than 90th percentile. And finally, the income category. The income category will show 5 categories. 1 is if the person's income is less than 10,000. Let me just. Okay. If the person's income is less than 10,000, and then And then 5 will show if the person's income is more than $100,000. So all of these are going to affect the person's decision to take risks. Your job as an analyst is to categorize. See, I have to take my time to explain each one of these factors to you, because if you don't understand these factors, you don't even know what you are doing. Your job is to classify these people. So to do that, you need to load a lot of Python packages. And if you don't know any of these packages, you may ask, or you may dig more into them. In fact, in one of the projects I have given you, I have asked you a question to explain every package that you, or every library that you actually load. The first is NumPy, we know it. Pandas, we know it. Matplotlib, we know it. Importing a CSV file, we know it. So most of these things are well known. Plotting, scatter plotting things, we know that. So from here, they are quite fun. Seaborn, we know it. You're going to use it. It's for data visualization, built on top of the Matplotlib, and then it gives you very high-level graphics. Okay, sklearn, it comes from that scikit-learn. Inside that is the standard scaler. It's very, very useful if you want to standardize or give them the same scale. It's very much used during pre-processing, okay, to standardize the features, because it has a zero mean and a constant variance. Also, importing date time is very, very nice toolkit that works with dates and times. If you want to use dates and times, you import that. Other packages for modeling purposes, because we are going to do k-means inside the sklearn library, we will import k-means, we'll import agglomerative clustering. That's another form of hierarchical clustering. Then we do the affinity propagation, which we did the last time. And then we will also calculate some other things, like the normalized metric, which is used to evaluate the quality of the clustering. It will correct the mutual information, from the study. And this package is useful, very useful when you need to compare clusterings with a different number of clusters. For k-means, you choose it ahead of time. Okay, but for others, you select it. And this is for that purpose. And then finally, this cluster covariance manifold of them, all of this will help you to generate some unique graphing for that purpose specifically within the clustering method. And also, you can check some correlations and covariations within the clusters. Now, the other helpful packages, so one of the things you will notice is that you must always load all your packages. You must know and load all your packages. Maybe you might not know. Some of them you will know in the process of doing the work. And you realize that, ouch, I need this. So you go back, install it, use it, make sure it works. Then you finally can now add it to the package section here. We know these tickets. You see these tickets, we'll talk about it. It gives you powerful tools that you can use to do your plotting. You remember when we used to plot, the last time we met, we used the same package, ticker, to plot so that it will spot the clusters, the centroids, where they are supposed to meet. And finally, we have this ITER tools. From that ITER tools, you can import cycle, which has values that can be accessed or iterated using a repetitive loop. So all of these packages must be ready before you do your work. Now, the first thing to do is to load your data set. Okay, so I have given you the data set. Let's just have a feel of the data set so that you are not completely lost regarding how does the data look like, where is the data, and things like that. No, I want you need to feel a bit of the data. So I'm going to see if I can open this data set, which is an Excel data. Yes, which one?
Please, you only give us the Jupyter notebook without the data.
That is true. I just realized, and you did not ask, so it's good. It's good. So let me show you. Let me give you. This is the data set. It is in a CSV file of which I've saved it. And the ID section shows the individual people. Okay, so we don't want to hold names. So sometimes when you're going to collect your data, you say that the people don't want to give to me is because you have not documented ethics to indicate to them that you're going to anonymize the names. Okay? You show them an example like this. I'm not going to use your names. I'm going to say ID1 for the person. So nobody will know who the person is. Or you can even tell them, you know what you can do? Just use an ID for each person, change that section and give me the data so that I don't know who it is. So you should write a beautiful ethics letter so that, you do not violate any ethical considerations. So this is the age of each person, but this age is not the age of the person, it's like age classification, education, marriage, case, everything that we looked at, these are the numbers. Everything is numerical data. If you want to know the end of the data, you click your control and then you click your end. And that will go all the way to the end here. And when you look on the left, you can see that we are talking about 3,866 data. That is it. That's the last person. So this is a large data, very powerful, useful data set. This data where you are dealing with individuals is very huge. When you're dealing with individuals transaction also is also very huge. When you're dealing with countries, we know there are 195 countries in the world. So that is not all that huge. When you're dealing with firms, that is huge, and things like that. So that's why big data analytics is a big deal. So there's a real life data, and these are all your information. Now, you got to save this data in your working directory, okay, with that name, because you're going to load it with that. Let's go to that command. So in our command center here, you will notice that we have processed the data. I told you the features are over 500. And now what you see are just some few features. So we have those attributes you saw for different investors, which shows a particular person's ability and willingness to take risks for the year 2007. This was a before crisis period. We're not looking at the post-crisis period. Okay, so this is the pre-processed data for the 2007. You go to this command here, and this command will load your data nicely for you. We have decided to call the name of the data set. Okay, and using the pandas, okay, we use this command to load the data set in the form of Excel. Now, the data set is actually in Excel. If it's CSV file, you have to change the command. Okay. But it's an Excel file, as you can see. It's an Excel file. Okay. So we are going to use, it's an Excel file. It's not a CSV file. Let me go to the home. Everything here is an Excel file. And now I'm showing you the screen for my Jupyter Notebook. You know, I toggle between this. So please, wherever I am, if you are not seeing the Jupyter Notebook, let me know. I'm sure you are looking at the Jupyter Notebook now, aren't you?
Yes.
Good. Yes. So we call the name of the data, we could have called it investors or process data clause, but whatever it is, we just call it data set. And this command will load the data set. You can see that the last time I ran it, I gave it a run command of 3. I'm going to run it again so that you all see how it goes. But before then, remember we have to run this first one, which I have. So let's go to that. The star means that it's running. Now we've run it, it's loaded. Okay. You can import this filtering command if you want. Sometimes you just do that to avoid any warning disabling. All right. Once you've done this, you can look at the type of data you have loaded. This is a pandas.core.frame.data frame. So that tells you that it's a complete data frame of rows and columns and headings and all of that. Great. Now you are ready to do your exploratory data analysis, your EDA. The first thing we are going to look at is we're going to look at the different columns and the different features in the data. That means you're going to look at the descriptors. To look at the shape of the data. The thing about the shape of, and I've asked you questions on this. The shape of the data is actually telling you the number of rows and the number of columns. So this 13 here, when you run data.shape, it tells you that, oh, and by the way, let me run it again. I just ran it as command 21 and it just showed the same. It shows that there are 3,866 rows or observations, and there are 13 columns or features. That's right. No feature has been identified as a dependent, no feature has been identified as an independent there. So that is what it is. Okay, so it means that the data, and I'll have to type this, and sometimes you see that a question will be asking you to describe your data, type all of this. So the data has information for 3,866 individual scores across 13 features. Self-explanatory. Now let's pick the data carefully. This command, okay, it will tell you how you want the result below to look like. For example, you want the results to display, you want it to stretch horizontally wider, or you want it to be a bit squeezed. So if you change this command, and then you show the head of the data, just the first 5 rows of the data, okay? This command, if you do it like 50, let's run 50, for example. You will see that it has spaced them accordingly. If you use 500, okay, well, it shows almost similarly. Okay, but it controls how wide the output display is in the notebook. Sometimes, if things are so jagged, sometimes it doesn't look nice. So by using 100, it puts everything in the right frame. Okay. The next thing, so this is just the head of the data. If you want to see your data, the moment your data here shows, it means that your data is nicely loaded. We can proceed. And from here, we can make a note that there are 12 attributes. For example, the ID is not really necessary. So the real attributes are the 12, excluding the ID, which is the individual. And you can see that we can categorize these as demographic. We can categorize them as financial and as behavioral categories. In fact, let me show you something. When you come to our notes here, okay, you will see that that is exactly what we have here. The attributes are demographic, age, education, marital status, number of kids, life cycle, occupation. This make up the demographic of the person. The financial attributes are house ownership, spending versus income, the net worth, the income. We looked at this. It's all there. You see, this one here is 6 variables. What you have here is, this one is 6 variables. What you have here is 4 variables, okay. Making it 10. And then what you have last, the behavioral attributes are 2, making it 12. The behavioral attribute is very important. Willingness to take risks and willingness to spend. This is a real thing that would define a particular person's risk profiling or being classified. All right, so those are the categorization or the attributes of this individual. Now, the next thing to do is to describe the data. And you already know that in Python, you can do descriptive statistics. But I want you to note that in Python, the descriptive statistics, let's run the descriptives here. Star means it's running. Okay, see, this one didn't really show up, which is cool. Sometimes they will not show the way you expect it to show. It happens. Let me just remove this. See. Okay, so it's showing now. Now the 3 here is simply controlling the decimals. Okay, so I don't know why the 10 didn't really show, but it is controlling the number of decimals. You can see that each one of these, the decimals are too many. So by using the precision, you are able to control the decimal places display. Let me see what I don't know why, for some reason, it is not showing. I can round. You can show the rounding inside the describe so that this one doesn't show. But that is basically what it is trying to do. All the same, you have the descriptive statistics. We know it. You can talk about it later because we've done this multiple times. But one of the things I want you to notice is that Python doesn't give you all the descriptors. So if you want to have that of the others, you need to calculate them on your own. And there are several other ones. For example, we don't have interquartile range. We don't have range. We don't have skewness. We don't have different kinds of quartiles. You don't have, what do you call it? You don't have ketosis. You don't have coefficient of variation. You don't have harmonic mean, geomean, and so many things. So you can individually calculate all of this. I put it there for you. Okay, so if you look at this, you'll be able to know, some of the things. For example, the average age classification is 3. The average age education is 2.9. So it tells you clearly. We spoke about married and being unmarried, okay, with a certain level of classification. We talked about kids. Okay? Some of them have got high kids. For example, look at it. The maximum number of children was 8, which means that some people have got plenty children. Okay? And the minimum number of children was 0. So many people too do not have any children. And the average number of children is almost 1. So majority of these people have at least 1 child. So this gives you a kind of idea about how the data is being described. And then you can talk about all of the rest. The next is visualizing some things. Okay, we can look at the correlation, but we'll later come back to this correlation. Okay, we can look at the correlation of the variables. Okay, but normally it's nice to look at this post-clustering. After the clustering, you can look at this properly. This command, where you set up to generate a correlation matrix of everything, you can use this to generate the entire correlation. Now, when you have this second one here, it's just how you want the entire correlation to be. But the command, the actual command is this. The actual command okay. And then you can now showcase your correlation. I don't know. Okay, good. You cannot showcase your correlation of this. Of course, I've zoomed it too much. But you will see that most of the variables are positively correlated. Okay, you see that here. For example, you have 0.76. There are some negative correlations as well. But of course, the color will tell you the level of correlation. Like I said, this is post-clustering that we can look at. But they're all part of the EDA that you can do. And you can see that there are some positive correlations here. In your case, you will have a question related to every action that you'll be taking. Let's prepare the data. So we are going to perform any necessary changes to the data, for modeling purposes. Whether you are doing supervised or unsupervised learning, this thing is always supposed to be done. So first you have to check. Why is this thing still running? Okay. So first you have to check whether there are any missing values, any null values. So this command will do that trick. Print any missing values within this name called data set and let us know. So you run this command, and if any value is missing, it will show. Run yours. I will encourage all of you to be running yours, okay, and be telling me what you had. So it's nice to run to see. So when you run yours, you're going to realize that there's null. The null values are false, which means there is no missing data, and the data is already in the categorical format, so no further cleaning should be done. Now remember that the ID column can be removed. The ID column, which is not needed, the individual persons, can be removed. If you set this deep, and this command will do that removal. So we just rename the data set as X, okay? And we call it, created a copy of this data set and call it X. And then we say that copy to a deep. So if you set deep to be true, a deep copy is made for each of the component variables. And so we create that, and then we drop the ID and we run the new data set. This is what you get. And so you can see that now the ID column is gone and everything is now a new data set. This X is something we can be using throughout the rest of the way. All right. We have to also check whether we can transform some variables, if there are any anomalies. For example, if some variables are not normally distributed, you can check that. So the data available is made up of attributes, which have similar numerical scale with no outliers. So we don't need any data transformation for this data. Everything is sorted, cleaned up already. So we are ready to now do our machine learning clustering algorithm. So the first thing we are going to do is to perform analysis and visualize the analysis. We are going to perform two different aspects of clustering, k-means and affinity propagation, just these two, so that you know. Please remember that you could be asked to do all the others as well. So let's start with k-means. What's the first thing you got to know? Well, in k-means, we look at the matrices to get a number of clusters, because remember, you have to select what clusters, how many clusters you're looking for. You have to choose ahead of time. Okay. There are several things. Remember, it is observations that you're dealing with. It's observations. You have close to 4,000 observations. You got to create a cluster mechanism for these observations. Okay. If you can remember k-mean, what you do is that you make some choices, and you choose the number of clusters you want ahead of time. But we're going to use the sum of squares errors within clusters and the silhouette score, which we employed yesterday. We're going to use these ones to be able to examine the entire work. So you take your software. All right. So we are going to look for the optimum number of clusters. So the first thing you do is to find the optimal number of clusters, followed by the creation of the model. Here, there are two ways, like I've indicated. Okay, two matrices. We looked at this the last time, which you are going to use to evaluate the performance of the clustering. Now, sum of squares, error, silhouette score. That's what you're going to use. How do you find the optimal clusters to use? We've already known that for this method, when the value is close to 1, the points are well matched. When it is around 1, they are disjointed between two classes. And when it is less than 1 or -1, when it's close to -1, like correlation matrix, it means that they have been misclassified into the wrong cluster. So we are going to use this command to check for the value of the sum of squares error. Now look here, we create a command called distortions of our data set. This distortion will store the initial inertia, okay, what we used to call the initialization, okay, for each iterations. It will track how the distortion changes across any particular iterations. We set the maximum loop to be 40. Now, normally 40 is the one that we take as the maximum number of iterations. You know, it allows you to stop over, iterating or over looping. In that case, going on and on and on. And so we set that. All of these are used to build up the k-means inertia, okay, so that you are able to store the inertia or the distortion values per any particular iteration. And then this will draw the graph. Okay. The 10 and 5 will specify how you want the graph to look like, whether stretching it vertically or stretching it horizontally. So the graph will also show the elbow effect. Okay. And the elbow effect is the one that is going to guide you to know how many clusters to select. And yesterday, also, the last time I showed you how the elbow effect is done. These commands will plot the distortions. This command will plot the rotation. These commands will show you the axis. And then this will show you the grid. Okay. And you can look at the elbow, where the distortion or the inertia stops decreasing rapidly. And when you run this, you're going to get this result. You should do yours and confirm that it is working. There you go. So you can see that you have the number of clusters to get all the way up to 39 and even beyond. And the question is, how many clusters are you going to select based on this? I told you the elbow. Now you got to look at it. Sometimes you might make a couple of mistakes, but there are some things that will guide you. So look at this carefully. If you look at this, where do you think the elbow starts from? Suppose you had no prior knowledge. Where does the bending actually begin? Ideally, it might look like the bending begins. Yes, which one?
I'm seeing 5.
Yes, ideally, it might look like the bending begins at 5. But there are two things that will help you to know that it's not exactly, because when it begins at 5, it also has not bent at 6. It's still at 5 at 6. It's still at 5 at 7, right? And then at 8, it looks like a new bend pops in. Do you realize that? I just hope that you see what I mean. So on the basis of that, the bending will be at 7 because it is still at 5 at 7. I don't know if you understand what I mean. It has not changed the bending. So anything in between where the second bend happens, okay, that is going to be the number of clusters to stop. Therefore, the number of clusters by this approach is supposed to be around 7. Again, this is what the k-means will be telling you. What about the silhouette score? This is what the SSE is telling you. What about using the silhouette score? If you go through the same process, okay, with silhouette score, you got to import the matrix, which will evaluate the clustering quality. Okay, this command will create an empty list to store the silhouette for different number of clusters. I've written that here. This K in range 2 with a maximum loop, it will loop through the potential number of clusters from 2, because 1 is not a cluster, from 2 all the way up to the maximum, but doesn't include the maximum. So you're allowing it to do that. Then all of these other ones will tell you, we've done this in our example. It will show you, so the first one will show you the number of clusters, okay? So you want it to tell you the number of clusters. The random state, we know what a random state was. Okay? It ensures reproducibility. The initial listing, okay? Remember, because these ones are many, that initial listing tells you that you should run 10 initializations, okay, that you can do. Sometimes you include something called n jobs, which uses all the speed of the PC, but I decided to exclude that. This second command will perform the actual clustering, the k-mean clustering, on the new data set you had called X. Then you can calculate the silhouette score on the fitted data. Okay. And when you do that, you can plot the results, you can show all the other things that you got to show, and this will become your work that you have. So look at this one too. And then tell me the bend and why the bend is okay. So using this silhouette score, not the SSE, where do you foresee the bend? Where do you think the elbow effect begins? Really? Why is it not at 4? Why are we not using 4 as where the elbow effect should be? Who can guess? Why is it not at 4? Because at 4, it rises again. That is why. Because you are looking at it in a decreasing order. So at 4, it rises again, and then it begins to fall again. Okay. So if you look at this falling, the actual bending would now be 6. Ideally, the actual bending will now be 6, which then slips to 7 as well. So it's all around that same figure of 6, 7, of 6, 7. That is where we can make the guess. So I've put a note here that looking at both charts, the optimum number of clusters seems to be around 7. There's no specifics, but it makes sense to be around a certain. So if somebody chooses 7 and another chooses 6, it's cool. But it's dangerous for a person to choose 99 out of the for almost 4,000, investors. So we can see that the number of clusters increases past 6. Here, the sum of the squares error within clusters plateaus off, and you can see that here, from here. And from the second graph, if you look at this second graph here, you can see that there is a various parts of the graph where a kink can be seen. And you saw different kink. The kink here is where you have the sort of the elbow. There's no much difference in the 7 clusters that was selected by the first one and this second one, which looks like 6 and also 7. But based on this, we can now say that we are going to work with 7 clusters in the k-mean. So our decision to use the k-mean will be based on 7 clusters. And this is sensible based on the data. All right. Now, what about now that you know that you have 7 clusters, you're going to run your k-means algorithm. You're going to run the analysis itself. And so you indicate that I have already told you that I'm going to use 7 clusters. So these are your 7 clusters. So you start with that. So what you are going to do is that you're going to create a k-means model with 7 clusters. You're going to fit that model. This is a command for running the k-means. Okay. This is the actual command that we normally use. And this is a fitting of the model. So you run that, ensuring that the k-means clusters are 7. Good. Now, once you've done the running, you have to remember the process. What the process does is that it does initialization, it does assignment. Okay. Do you remember the steps that it uses? It does initialization, it does assignment, and then it computes the centroids through the assignment and then does the repetition. Okay. It computes it repeats the process, it iterates the process to them. So that's the same thing. The assignment is done here. So here you assign each group cluster to each individual in the data set. Remember, you have 7 clusters. And this assignment is used later if you want to do exploratory data analysis to understand the behavior. So how do you do that? So we're going to extract the labels. So based on this k-means here, remember, we are still using the data set. And we are going to create or extract the labels that we want. We want the Python to do that. So we'll run this extraction of labels here, for it to extract the labels. We'll use that when we come to our final approach. It's done it already. And we'll look at it pretty soon. But there's another method we can use, which is affinity propagation. So let's start with that. Now, the affinity propagation is here. There are a lot of things that you will see. For example, you write AP. AP is a name we are giving to the affinity propagation. Affinity propagation requires some few things like damping. What does that mean? It tells you how much of the previous iteration messaging, how it changes, the values, how they are retained. So the retaining values is in the range of 0.5 to 1. So in this case, we take the minimum. Lower values shows that it is closer to 0.5. So that means that, like, when you have lower value, which is like 0.5 or anything close to 0.5, it means that the speed of convergence is high. Okay, but that will also cause some sort of oscillations. It's like you are trying to make sure that the thing will converge well, but you don't want it to. It's like when you're applying brake to a car. You're applying the brake, but you don't want to apply so much brake so that the car will somersault. Like that. Now, the maximum iteration is 250. That is a maximum number of iterations before there is no convergence. Sorry, before you stop the convergence, because you want to achieve convergence in that regard. So the maximum number of iteration is 250. And then this affinity, that is a Euclidean distance that we spoke about. It is the one that is used to measure similarity between the points. If it is not using that, you can use something called pre-computed. It's an alternative, if you don't want to use the Euclidean. This command will fit the model. Okay, it will automatically determine the number of clusters by. Remember, affinity propagation, you don't need prior knowledge of the clusters. It will do it for you automatically. So it will automatically determine the number of clusters by passing the messages between points until you achieve harmony. And then you have this command here, which will assign each data point in our data set, which we now call X. It will assign each data point to one of the identified classes. We don't know the classes yet, but I will assign it. It will give them labels. Then you come here. What's the next one? Cluster center indices. Okay, that will give you the indices of the cluster centers in the original data set. It will give you the indices. And then the labels is an array where the element represents the cluster assignment. You will see all of this when the results show. The N clusters here is the whole running of the model. Okay. So this will calculate the total number of clusters by counting the cluster centers within. And then this print will print the entire result. So we run this. Let's run it. This star means that it's running. I mean, you guys have already run yours, so you would have known by now. I don't know why this one is delaying a bit. Anyway, you guys did a running, and you saw that I gave you 161, isn't it? Ah, there you go. Gave you 161. What does this mean? It means that he's telling you that you should form 161 clusters. Can you imagine? So out of your number, you want to reduce the cluster. You want to bring the thing into groups, and you're telling me that I should have 161 groups. So the affinity propagation is giving you so many clusters, so large, which will make it very difficult to know the proper differentiation between them. Very, very difficult. That's a whole data set on this one. You are grouping people. You don't want too many groups. If you look, for example, recommendation system that Netflix does, it has what? It has movies like action, it has comedy, it has thriller, it has, they are not that many. You can count them. It has comedy, it has thriller, it has mystery, it has science fiction, and then, some few other ones. They are not that many. They are not more than 20. So for even though there are several kinds of movies in the world, all over in the world, thousands, in fact, millions of movies, they can all be, clustered into not more than 20 groups. So for you to tell me that ones that are not even millions, these are just almost 4,000 people, you are clustering them into 161. That is too huge. So we need to evaluate. Which one are we going to use? Are we going to use what the k-means said, or we're going to use what the affinity propagation said? This is where the evaluation starts from. So we're going to check the performance of the k-means and affinity propagation using the silhouette coefficient. If the silhouette is higher, then the coefficients means that if the silhouette is higher, it means that the model is high. The model is well classified. It's been able to do the clustering properly. So we are looking for those one, whether k-means is giving us a higher silhouette coefficient score, or the affinity propagation is giving us a higher silhouette coefficient score, because that is the one whose clustering approach will be selected. So we'll come here and run this. So we're telling the software to give us print out km. That is a k-means, okay? And then print out the AP, which is affinity propagation. Give us the silhouette score for each one of them, given this data set and all the things that you've done. Both of them are using the Euclidean distance. And this is the answer that we get. Let me run this again. There you go. So you can see that the k-mean give us what? Almost 17%. And then the affinity propagation give us almost 10%. So you can see that the k-mean score is higher than the affinity propagation score. Okay. The silhouette coefficient score is higher. Okay. More so, you can see that we've already said that there's a large number of clusters that affinity propagation gave us, which is not sensible or is not comprehensible. Okay. So in this very example, if you have fewer clusters or fewer categorization of investors, it's good because you are able to build a simple and standardized investment management process. You can make your life easier. You can make their life also easier. That's it. So we have information for our client. What we have built here, the financial advisor is going to look at it, and then they will make some managerial or manageable intuition about how many clusters they should have. We need to understand this and then explain it to them. You are a business analyst. a data analyst, a data scientist. Okay. You need to understand this and speak that language to them so that they can tell their investor types. And this is more practical to deal with 7 investors than to go for all investor profiles more than 100. Okay, so we are settling with what? 7. Hallelujah. Now let's get intuition. Now that we settled on the fact that how are we going to do the classification? This is a real deal. We are going to check each cluster. Remember now we know that we are going to have 7 clusters, right? Okay, so these are 7 clusters, 0 to 6, which is. We're going to check each cluster. We're going to understand the intuition behind the clusters. Right now, the clusters are in the form of 0, 1, 2, 3, and all of that. But what is the intuition there? What does a 0 here mean? The people within the 0, what is around them? What makes them fall into the 0 group? The people within the 1, what is their characteristics? What is making them? So that you are able to find those behavioral characteristics, those specifics. And now you can know which ones have got the willingness to take risks or not. So the first thing we're going to do is that we're going to plot the average of each variable of the clusters. So instead of individual human beings on the far left here, where you have up to almost 4,000 human beings, ID all the way up to that. Now we are going to deal with only what? Clusters. And then we find for the age, the group 0 people. Okay, what is the average age they have? Now look at group 0. You will see that the group that has got the highest average age is group 0, which is 4.8, the average age. If you check group, which group has got the lowest average age? Which group? Which group has got the lowest average age?
Group 2.
Which group has got the highest number of kids?
Group 1.
Group 1. Which group has got the highest highest number of houses? Which group?
Group 1.
Group 1.
So you are getting the point. So, but you see, by you tell, so now you are not talking about individuals again. You are speaking in terms of groups. So now we can fish out the demographics, and then let's go to the demographic features. Who are controlling? Who are having high of the demographic features? Now the first, so we have to plot them. So you're going to plot the results, and the results are based on the means we have already had here. Okay. So let's take, for example, age. So we are plotting all the demographic features: age, education, married, kids, life cycle, occupation, and all of that. These are the demographic features. All of these demographic features, we are going to plot their for each group. So when you take group 0, group 1, group 2, group 3, all the way up to group 6. Now, based on the graph, the bar plot that we have drawn, you can tell which group has got the highest life cycle. Which group? And I know colors are working, but also bars are working. Which group has got the highest life cycle?
Group 1.
Group 1. Which group has got the highest number of kids? Average.
Group 4.
Good. So now you can tell that some people have got highest number of life cycle more. You know, so when it comes to those who are doing well, when it comes to life cycle, you can see that group 1 here and group 2 here are really, really doing well. You know, when it comes to the life cycle environment. When it comes to the kids, those who are doing very poorly, when it comes to kids, okay, or not poorly, but those who are having the smaller number of case on average, group 1, group 2 are leading in those arenas. Okay. So by using the demographic, you can find some few things. So these are some of the things you can find. Okay. That the plot shows the average number of attributes of each group, each clusters. Comparing group 0 alone and group 1 alone, these two. Okay. Cluster 0 has a lower average age. And you can see that, okay, in blue, if you compare it to the blue, just between 0 and 1, 0 has got a lower average age, and yet it has the higher average education. If you look at the orange, the education is higher. So the age, the age is lower and the education is higher, which is interesting. In terms of marriage, look at the marriage, the green section, between just 0 and 1. They are almost similar. Okay? These two clusters are similar. So the individuals in cluster 0, I'm just comparing 0 and 1. The individuals in cluster 0 will, on average, have higher risk tolerance compared to those in cluster 1, just based on demographics. Do you understand? Do you understand this conclusion? Who understands this conclusion? They will have a higher risk tolerance. In other words, they can tolerate risks than those in the group cluster 1. Who can tell me why? You see, this is where your understanding of the data makes sense. Who can tell me why? Do you remember what the age stands for? The age, do you remember what it stands for? It means that those below, for example, lower age are those below 35 years. And you can see that, have you observed that most people that are older, they are very careful of taking risks. Have you observed that? And the younger generations rather tend to take more risks. Have you observed that or you haven't? Like the older people seem to be more afraid to go and climb and die or sort of thing. Anyway, so that is it. And then you can see that a person with higher average education, any person with a higher level of average education, that person is likely to take more risks. Do you agree with that? For example, if you go and check the stock market, the currency market, the people that are taking the stock market and doing the currency market and things like that, these are people who, on average, have a sort of a higher level of education. But the person without that much higher level of education, they are very, very careful. You tell them to go and put their money in stocks. You tell them that, no, I don't want anything. They want to see cash and things like that. So that is a conclusion you can make just between group 0 and group 1. And you can go ahead and do the same thing between any other group. You can take them one by one and compare that. Anyway, that's based on demographics. Now let's go to based on financial features. That is the willingness to take risks. So we are looking at the financial and behavioral attributes. You remember that we are plotting all of them together. Because the first one, the demographics was long. But this one, if they were all together, if there were not that many, we would have plotted all of them at one go. But otherwise, it became too, confusing graph. So anyway, so we can now plot these ones together. So look at this graph and take the green color. Okay. Take the green, or let's take, which one is the net worth? I mean, if you look at the blue, it's very, very funny, right? with the housing and all of that. Anyway, so the plot here shows the average value of the attributes for each of the clusters on financial and behavioral attributes. I'm supposed to just put some thing here. Let me just plot this. So once again, look at group 1 and then group 0. You can see that cluster 0 has got a higher average house ownership. Okay, they own most of the housing. You can see that cluster 0, you can see that compared to cluster 1, the blue, if just comparing the blue colors between 0 and then 1, you'll be able to note exactly that the 0 cluster, have got a higher blue color, which is a average house ownership than the 1 cluster, the cluster 1. But not only that, if you check the orange color, you will see that 0 is doing more on the orange. The orange here is the average net worth. Okay, the average net worth and income. If you check the green, the same thing, the income, the same thing. You see that the group 0 is doing better than group 1. So they have higher levels. And then if you check taking risks, remember that risk factor was this brown one. They have got a lower willingness to take risks. Unlike group 1 or cluster 1 that's got a higher willingness to take risks. Now look at savings versus income. Okay. The purple, they are similar. Okay. So the point here is that if you compare the savings as its income comparison and willingness to save, the 2 clusters are comparable. They are similar. Okay. For the purple color, they are all similar between 0 group and then group 1. So what is the conclusion here? That when you take these other factors, financial and behavioral attributes, we can conclude that the individuals in cluster 0, on average, they have a higher ability and lower willingness to take risks. You can see that. They have the lower willing, they are not that willing to take risks. You can see that in all of the colors compared to those in 1. So we can see that those in group 0 have got the ability. You've got ability to take the risks, but you are not really taking the risks. You've got everything for you to go for it, but you are not going for it. That is one thing you will observe from here. Okay. So, of course, you can also generate heat map for this, but the heat map eventually wasn't anything big deal. You can now do the analysis we've done here between 0 and 1. You can do it between 0 and 2. You can do it between 0 and 3. You can do it between 0 and 4, and all along like that. And then when you're done, you can do it between or across the rest of the information here. And now you can generate a sort of a heat map. And the heat map will tell you which people seems to be mingling along. So if you look at cluster 0 here and cluster 1 there, and you will see those that have got a similar coloring in the work. So if you combine all of the information together, from the demographics, from the financial, from the behavioral, just for cluster 1 and cluster 0, just between the 2 of them. If you look at the overall ability to take risks here, for cluster 0, if an individual is within cluster 0, that individual's ability to take risks is higher than anybody who is, on average, than an individual in cluster 1. And why is that so? Because you can see that an individual in cluster 0 here, the whites are not that many compared to the white in the one in cluster 1. Okay, you can see that here. There's more blacks, I'll put it that way. There are more blacks in those in 0 than there are in those in 1. So you got it. This is just for between 0 and 1. And of course, like I said, you can do the same thing for all the rest. And when you do the same thing for all across clusters, we can summarize the results in the table below. So you got to go through each one of them. And now you can say that the risk tolerance column. And now let's look at it. So we look at cluster 0 now. You look at cluster 1, you look at cluster 2. You can, your whole thing is that you're going to assign who has got high risks, who has got low risks, who has got medium risks. So if you check the column here for the risk capacity, we've indicated that the risk tolerance shows the subjective assessment of the risk tolerance of each of the clusters. So let's take cluster 1, based on what you said. It has low age. The ages of the people there are low. They have high net worth, high income. They are less risky. Okay, they have less risky life category. They have the willingness to spend more. So because of this, they could be classified as what? High. Now remember, this is intuition. Intuition based on the graphical analysis, based on the mathematical analysis you've done. We can now classify them as, they belong to the high risk capacity group. Now, why? Well, they are children, more or less. They are not children, but they are low age, and they've got high net worth of income, less risky life category, willingness to spend more. That way, the willingness to even spend more. Okay, they've got a high capacity. Now, let's take something like low. Then you can appreciate. Let's take group 6, cluster 6. They are low age. Okay, so at least they should have been high, but medium income and net worth. And here's the point. High willingness to take risks. Okay, many kids. That is serious. When you have many kids, your decision to take risks is not usually good. And why is that so? Because that's why when you have children in your car and you are driving, you don't want to do overtaking anyhow. But when you're alone, you have no child in the car, the way you drive is different from when you have children in the car. I hope you guys understand. So when they have many kids, and then they already own their house, what are you telling them again to do? They are very careful, okay, to take some actions. So you can go through the rest and then you can see that. Now this table was created with this. Okay, I use this approach to create the tables for each one of this. So when you are creating tables, you don't need to necessarily create tables. You can do that easily in Python. So what is your conclusion here? Here's a conclusion. One of the key takeaways of all of this exercise is that we have been able to use K-means. The approach is helping us to understand the cluster intuition. We have used visualization techniques. We have understood the behavior, expected behavior of each cluster member. We have used both qualitative information, to interpret the mean values of the variables in each cluster. We have demonstrated the efficiency of the clustering method. That the clustering method can help us discover, the natural intuitive groups of different clusters based on their risk tolerance. We've been able to do that. So now you have these groupings. You are going to speak in managerial terms. You're going to create a board. But you see, when you go, what you're going to tell them is this. This final one is what you're going to tell them. But they don't know behind the scenes, there is a lot of work that has gone into coming out of these clustering approaches. Now, given the clustering algorithms, given the fact that it can successfully cluster investors based on different factors like age, income, and risk tolerance. It can further be used for portfolio by portfolio managers or investor, company investment, asset portfolio investment companies like Goldman Sachs, like McKinsey, like JP Morgan. They can use that to understand the investor's behavior, and then they'll be able to now categorize and standardize the portfolio allocation and the rebalancing across every clusters that they are doing. It makes investment management process very easy, very effective, very easy, very fast, because now you can do. Other than that, you are going to think about all of these groups. It's crazy. It's crazy. You're going to think about 3,800 and something people one by one, when you could easily think about 6 groups of people one by one. You just have to understand the 6 groups of people. And once you, because people behave the same way. People behave the same way. When you ask the behavior of some group of people, they are all behaving same. Human beings are repetitive in their life. When a person is buying a car, it gets to a point the person is advised to not buy cars because cars will depreciate, so you should buy a house. So they move in the same direction. When a person likes flying, and he flies a lot, he's more likely gets to a point he starts flying business class. And it's the same thing with anybody that follows that same pattern. There are groups of people who will like women. There are groups of people who will not like women. Majority of people will fall in between this. So you get to know that the clusters are what? The clusters are simple. There are groups of people who want income a lot. There are groups of people who don't want incomes a lot. There are groups of people who will fall in between, and some people are a little above in between, a little bit. They are, so when you have millions of people, it's possible to get some similarity that you can use to index. Ladies and gentlemen, that brings us to the end of the entire Kabudo. Any question, please?